Hello, and welcome to our 11:30 media availability with Thomas Zurbuchen, NASA Associate Administrator for the Science Mission Directorate. Dr. Zurbuchen will give a short presentation, and then we'll open it up for questions.
Yeah, so happy to be here, and mostly spend the time answering questions. And if you don't have any, I will ask. Yeah, that's what we're going to do. So what I'm going to talk to you about is a view of my mission director, the Science Mission Directorate, after something like 2.5 months on the job. So I, of course, have been working with NASA for the last 20 years. I've built instruments that have flown on spacecraft, for example, to planet Mercury, or are still in flight around L1. Many of these instruments are observing the sun or its output, the solar wind, on a day-to-day basis, and papers are being written about from these data and are presented here. I think if I counted correctly, something like 25 papers just on some of these instruments, just the Messenger and the ACE. Those are, spacecraft. Those are two spacecraft that I spend most time on. So this is the exciting part of one of the many facets of the Science Mission Directorate, which is that we're learning about the fundamental science that drives our universe, our Earth, and everything in between. And so these are the three topics that are really at the center of our Science Mission Directorate, and I just talked about expanding our knowledge. I just want to stress that in every single element of our portfolio of missions and directorates, expanding our knowledge about the knowledge of nature, about the processes that drive our environment, the solar and space physics, how the sun interacts with the Earth and interacts with our technological society, and also with our planets, the processes that were at the heart of the formation of the solar system, and also relate to some of the simplest questions but the hardest questions to answer, which are, where are we from? What are we alone? Questions like that are really just so important part of what we do at NASA. Overlapping with this, but very specific, is a type of theme that is here at the top, which is safeguarding and improving life on Earth. We do a lot of work that has impact in weather forecasts tomorrow, today, predictions about how the Earth system evolves on a 1-year or 10-year or timescale or beyond, and also helps us save lives every day. There's all kinds of programs that relate to that. Another topic that we're spending a lot of time with is really a convergence of 4 different sciences that used to be in its own buckets, but they're converging together and really relate to the search of extraterrestrial life. We're at the verge of really important new knowledge that we're getting there. The first science, of course, is what we learned on Mars. The other one is also in planetary, the icy worlds out there, the water worlds out there around the giants, moons such as Europa, Enceladus, and so forth are in that. So it's that second bucket. The third bucket, of course, is astrophysics, where we observe many planetary systems, several thousands now, and we have observed Earth-like planets, many of those as well, and that's all very recent. And the fourth science, of course, that goes without saying is really in biology. We do a lot of work. Most of the funding in that space is not by NASA, but it's really converging in work that we also have in some of our programs, which really are looking at the early stages of life. So these are the 3 topics, and of course, I'm not going to talk about the whole program, but just want to talk about 2-3 aspects of it. And this is one aspect I'm going to start with, and it really is a story that's in July 2016 and starts with an illegal campfire that evolved into a wildfire in California's state park, the Garapata State Park. The wildfire was growing so rapidly because, of course, the high temperatures and the low humidity that the blaze grew, and it took 3 months to get the fire to stop. And by the time everything was said and done, an area 5 times the area of San Francisco was devastated by that fire. and with an estimated damage of $230 million for that fire alone. So why do I'm telling you that? We're not the operational agency. Of course, there's many, NOAA is doing really important work, and we're working with NOAA very much. But as we went forward through this fire, our 3 assets in space, the Terra, the Aqua, and the Suomi NPP satellites were providing data directly to the firefighters in a way that the battalion chief at the Riverside County Fire Department basically said that we were his eyes on what happened, and without that, he said, he could have not done the job as well as he did. This is the kind of stuff we do on a regular basis out of NASA. Of course, after the fire was over, the work starts, because you have to decide how you're going to now deal with the debris and the environmental challenges that come there. And again, NASA provided information for that. The knowledge that comes to where humidity is in the ground, where the dangers are, and so forth, is an important part of monitoring the Earth as part of a system, and is part of missions that are flying right now or are in preparation. SMAP, for example, is a mission that's out there and doing these measurements on a day-to-day basis. So while these fires are a concern, there's many other threats that come from nature. As beautiful as nature is, there's threats. And this is, of course, a picture, an IR picture of Moore, Oklahoma. And it's after May 20th, 2013, where a tornado ripped through this environment. This tornado that left 24 people dead, even though there was a warning of 16 minutes ahead or so. That, of course, came by NOAA. So the reason I'm telling you that story is to talk about the second way NASA interacts with these kind of environmental challenges, and that is that just a few weeks ago, on November 19th, we launched the GOES-R satellite. And on there is, for the first time in an operational use, the geostationary lightning mapper. That mapper will provide unprecedented predictions for tornadoes that are forming in the entire U.S., and will provide these predictions based on a new instrument that was developed in our programs over the last 20 years or so. The first RNA programs that led to technology development, which are now part of this operational tool. These mappers, this mapper will really provide information about the formation of these tornadoes as they grow. So this is a second way we're providing, besides the detailed fundamental research that I talked to you about at the beginning. The first one is operational support, and with our assets, and to really develop the tools for operations in the future. So there's actually places where we have important tasks that relate directly to operations, and one of them is in the Planetary Defense area. Actually, I'm not going to talk so much about it. Ask questions if you want to. This is just a picture taken over Russia of one of those rocks coming down. It's actually a really small rock. The good news is, for the big rocks, kilometers or higher, we have 90%. We have cataloged. For the small rocks, we're not doing so well yet, because even though this team has put a lot of effort and actually over the last years have increased the investments towards finding all these rocks that could devastate, cause massive loss of life and so forth. And so we're at 27% or so of rocks that are at 140 meters or so. As I said, at the kilometer and higher kilometers, we're at 90% of these rocks. So this is a tool that we're actively part with FEMA, and really part of averting catastrophes where they come out of the sky like this. Another type of catastrophe at the beginning could look really beautiful. It relates to space weather. Space weather storms, of course, are a reality. There was aurora observed just last week. Even though the sun is relatively inactive right now, these auroras were out there, and they're observed out in this case from the space station. But strong space weather storms could really devastate, systems such as the power systems or satellites that are flying. Again, this is work we're doing both on the fundamental side, but also the side that actually helps NOAA predict, provide these warnings. All right, so The second theme that I'm going to talk about is focused on the questions, are we alone? And it really starts with on a day in 1995 where at a conference in Rome, pretty explosive announcement was made, which is that two scientists basically announced that they found the signature of a star that basically showed that there are planets, a star that was is not our sun. Another star was, and that announcement in 1995 really led to an avalanche of discoveries, and that are now part of missions that are already flying, Kepler, for example, or missions that we're going to launch that are looking at finding planets around other stars and also exploring those planets and of course finding cousins to our Earth, which are planets in habitable zones that could do exciting work. We have close to 5,000 of such systems already observed, and dozens of planets that are in the kind of habitable zone. And so this is just work that is just really super exciting. James Webb, when it launches in 2018, of course, will do important work on this as well. Well, at the same time, I told you on the inside of our planetary systems around the sun, the habitable zone, right, where we looked at, of course, were, it's the Earth. We know a lot about life on Earth, thank God, right? But what happened since 1995 approximately as well, and the reason I'm pointing to that is because I want to give you a feeling that we're really talking about like 20 years of fundamental research. It's also just about that same year where we really found, using gamma ray and neutron observations, that there's large amounts of water, and proof that on Mars and also water on the moon. At the same time, we also found water in other areas, and actually even at the poles of Mercury. And so basically, it's these that kind of the water prevalence everywhere in the inner solar system at terrestrial type of planets is accompanied by another set of astonishing discoveries, which relates to the fact that Europa, for example, is an ocean with ice over it, and an ocean that on the inside touches rock. So it looks very similar to some of the areas we think overall as the Earth. There's other moons out there like Enceladus that spurt organics into space on a regular basis. And so what's happening is the entire discussion about where there's habitable Earth, of course, has made major progress forward, and has really become super exciting, and is driving missions today, missions that are already happening, but also missions that are in our portfolios of the future. So I don't know what the likelihood is of finding life both in our solar system outside of Earth. I don't know what it is elsewhere, but I know since 1995, when we did this, when this kind of research started, it may have increased, that probability may have increased by a factor of 100,000. So the kind of that, it's really an incredible trend that we're seeing in the last 20 years, and we can only guess where we're going to be in 20 years from now. So that's what we're doing. I talked to you about the fundamental research, the safeguarding and improving life on Earth, and the search as part of this, and the search of extraterrestrial life that is really absolutely exciting right now. So what I wanted to do is stop here and just turn into a Q&A type of session. Does that make sense?
Sounds good. Thank you. Okay, and we will start over here. Again, only reporters in the room. If you have a question, please raise your hand, state your name and affiliation.
Sorry about that, Nancy.
No.
Hi, I'm Alexandra Witze with Nature, and thank you for that overview of the current status of the Directorate. Could I ask you to talk a little bit about your priorities and themes for 2017 going forward? What are the major things that you hope to accomplish in your new position? And also, if you could address that in the context of the change in administration and then the uncertainties that you spoke about in town halls this week.
So when I came in to my position, I really thought of the priorities for my work to be priority of 3 priorities. The first one was to get to know the team and build the best team that I can within NASA and with our organization. So I spent the last 2 months actually sitting there, meeting with people, and really getting to know that, because I do believe, even though that may not be the most obvious answer first, that it's the quality of your team that in many ways helps the quality of your programs, right? I mean, the second thing then is to really focus on accomplishing success in our missions that we have, the ones that are under development, the ones that we're flying right now. So I spent, for example, in the first 2 weeks about 10 hours with James Webb, because that is such an important mission that needs to be successful. Now, I'm not the most important person in James Webb. It's these people who are touching this spacecraft every day, but I want to basically understand in what way I can support that group and basically have them bring in that amazing spacecraft in on cost and on schedule to do this. So that's my second priority. And then the third priority is together with my team now develop and lean forward and look at what's out there. I'm just starting that phase, and so what I can tell you is kind of the principles I'm using to develop these priorities and the vision going forward. The first one is that the science that we're doing is actually not science that I'm supposed to invent or kind of prioritize primarily. We have the National Academy for that. So it's my full intent to use the National Academy's prioritization and input to guide what we're going to do in the future. So that's principle number one. Principle number two is that I believe that our science should be ambitious. And I believe in the confluence of ambitious science and innovative technology. So you're going to see a lot of me talking about this. I believe that missions that we're building right now already do have, but should have in general, should have the opportunities of bringing new tools into space. For example, whether that is by launching a small satellite with it, whether it may be a CubeSat or something like that, or a bigger small satellite. We see a lot of important work there, for example, in earth sciences, from both commercial partners and others, kind of figuring out how we leverage this and do the best job for our science community and the United States is one of the priorities for me. So it's kind of really that ambitious science and innovative technology that also could be processed. And I think the third one is also really to stick to the amazing tools of science. I really believe that as we go forward, and that doesn't sound very strategic, but I want to say it out loud, which is that this NASA, our agency has been the strongest when we're looking at what's in front of us opportunistically. We see what is there and go answer the biggest questions that we see, that we find. We're a research agency that explores in areas, that kind of questions we're looking at today. Even just a few years ago, were not questions that were in the forefront of our minds. The Enceladus observations, Jim, what was it, 12 years ago? About, that we're now thinking a lot about. I talked about the 20-year time scale elsewhere. So kind of we want to opportunistically look at, with the Academy, look at what the new questions are that we could do, and both increase what we know about nature, but at the same time also help utilize what we do to the benefit of society. So those are the principles, more to come.
And if you could address how you do that in the context of an administration change.
You should know, let me just answer with an anecdote first. So I basically came in, and it was clear that we needed to prepare information for the next administration. I worked with my team to reflect, using these values to reflect what SMD is doing. And we put together white papers and information, and we deposited that. Then the elections came, and I was asked, do you want to change anything you did, for example, in earth science? And I didn't change a single word, because the principles that I drew out are the principles that I would use in any administration, no matter what it is. So for me, I want to stick to those principles, just the same way I talked about in the town halls, right? Really focused on the data that we get, not amplify the noise, and behave like scientists, in which we and talk about scientists passionately, and talk about science in a way that we know is affecting life on Earth every day, the way I talked about, but also is building a great future through opportunities that are not predictable right now. Many industries that we have out there have grown based on investments in the science programs, and nobody would have guessed that would happen. You know, what you're carrying around in your pocket, you know, on your phone, is a lot of space data at work for you.
Are there any other questions from reporters in the room?
What potential do you see for small sats or CubeSats to benefit science?
So you may know that I ran a study for the National Academies before I took this job. And in that study, we looked at this very question. And the study was really clear in its our answer to that question, and it said that there is important science that can be done with CubeSats and small satellites. So, and now the level of which, you know, how many questions can be answered, important questions, depends strongly on the discipline. It turns out that, for example, solar and space physics, or heliophysics as we refer to, is a science, and if you look at its strategic plans, you know, by the academy, you look at this, you basically realize that many of the solutions are large N solutions, those N being the number of spacecraft that are involved. To map out the magnetospheric processes, you need many measurements. It's kind of, it doesn't help to have a mega spacecraft in one place and look at it and to kind of understand the large scale evolution of this system. And so for that, small spacecraft are a very ideal tool, and that's what the report said. Earth science has applications like that too. Many spacecraft, constellations of spacecraft, they're referred to high time resolution observations, for example. So basically what happens is that just because of orbital dynamics, a single spacecraft can overfly a given spot every X days or X hours, you know, depending on how high you fly and inclination. It may be every 4 days or every 2 days. Well, with many spacecraft, that can be done a lot more often, as we're learning from Planet Labs or, you know, commercial providers, but also from spacecraft that we're building in our own portfolios. Our venture class mission, Cygnus, that's waiting for its launch, hopefully tomorrow, I was just told. Tomorrow morning, the launch window opens with 8 spacecraft that will create much shorter revisit times over hurricanes or cyclones that are out there. Again, using the tool of many spacecraft to answer a science question in an ideal fight. So there is a lot of opportunity. It strongly depends what community to basically recognize how many such opportunities there are. In heliophysics and earth sciences, they're absolutely clear and obvious. Planetary Sciences has invested in small spacecraft as well, because there are some targeted missions, different lines of sights that can be done with small spacecraft in a way that we wouldn't be able to afford if it were ginormous spacecraft of the type that we normally fly there, you know, and we can go right along and solve a specific question using a very dedicated, focused investigation. And so in astrophysics, you know, the type of observations that have been talked about by the community are either point and stare type of observations for a given environment, or constellations of radio type of arrays that could look at radio emissions of the galaxy that are not accessible from Earth. So there's many opportunities, but not all of our science questions are usefully addressed with small satellites at this point. So I don't believe that in, let's say, 5 years or 20 years, all we do is small spacecraft. It's just not the way it works. I just really believe that there are certain problems that want to be addressed by a large tool, and we want to use those for, you know, those large spacecraft for those problems.
Are there any other questions from reporters in the room? Are there any questions on the chat this time? Okay, great. That concludes our media availability. Thank you very much.
Thanks so much.